Welcome, one and all, to the High Pressure Podcast. My name is Jeff Beamish. I'm an air quality meteorologist at Sonoma Technology here in the beautiful San Francisco Bay Area. As always, joined by my fellow air quality forecasting colleagues, Patrick Zahn, lead air quality forecaster, Steve Irwin, air quality forecaster, and gentlemen, we have a special cameo from our data sciences department today. We say hello to Crystal McClure, atmospheric scientist here at Sonoma Technology. Ozone season, it has arrived. Congratulations, everyone. We've made it through the winter. This is where you can give yourself a round of applause as well. So, yeah, ozone. It's obviously a thing as we get into May, June, July, and the warmer summer months. But we actually had an interesting ozone scenario play out on April 13th of this year in the Sacramento region. You're taking a look at the MODIS Terra satellite image from April 13th, and widespread cloud cover prevalent across California with a storm system off the northern California coast. Scattered showers occurring on this day with temperatures only in the 40s and 50s. And you take a look at this satellite image and you think, well, what's so remarkable about this? Obviously, it's interesting from a weather perspective, but why is the High Pressure Podcast talking about low pressure? This is why. The daily maximum 8-hour ozone concentration values from April 13th, anywhere you see yellow, that is moderate ozone AQI that was recorded in the Sacramento Valley, and some areas were near USG territory, up by Sutter Buttes, also in the Woodland area, and into the Sierra foothills. So, what happened on this day? Something called a stratospheric ozone intrusion. We're going to talk about what a stratospheric ozone intrusion, or SOI, what that is, the weather conditions that played into this SOI on April 13th, and whether these events can be predicted. So to start off this entire discussion, I want to go back to something that I had heard from a NASA scientist several years ago at a conference, and he perfectly summarized ozone to me in 5 words. Good up high, bad below. So what does that exactly mean? Ozone is good up high in the stratosphere because it's naturally occurring, and the stratosphere is well above our heads. That stratospheric ozone is naturally occurring. It also filters out the UV rays from the sun. So that's the first part of good up high, bad below. Ozone is obviously not great here at the Earth's surface because of the chemical reaction between warm temperatures, sunlight, and emissions that come from factories, vehicles, and of course, wildfire smoke can also play into ground level ozone formation, very harmful for your health. So that's the saying, good up high, bad below. But what happens when the good reaches the bottom? To talk more about that stratospheric ozone intrusion, the mechanism behind it, I'll turn it over to Crystal.
So to understand how stratospheric intrusions work, basically you have a fold of that stratospheric air, that good up high ozone is being pulled down to the surface, like we're seeing here with these red colors across the US. This is just an example from 2012. So you're getting all of that good ozone from the stratosphere, pulling it down to the surface, making it bad ozone that we end up breathing. This usually happens around low pressure systems and cold fronts that happen in the winter or spring here on the West Coast.
Yeah, thanks, Crystal. This is a really interesting animation to watch how it ebbs and flows and can get brought down to the surface through different dynamics that happen in the atmosphere. I was recently reading that stratospheric ozone accumulates during the winter and spring, so we're really in the peak time of year for one of these to occur. It doesn't usually enter into our daily forecasting because it is more rare, especially down at our sea level forecast locations. But can you speak a little bit to the climatology of stratospheric ozone and why it is more prevalent during the winter and the early spring months?
Yeah, that's because, at least on the West Coast here, more of our cutoff lows and fronts happen in the late winter and early spring. Usually in the Intermountain West region, we're typically looking at late March, maybe April or early May. And while it's more common that this is happening at the higher elevations, we do sometimes see this at ground level, like we saw in Sacramento. this year. And then also places like Las Vegas have documented stratospheric intrusions that happen at the surface.
And I wanted to jump in with a quick comment. Although it is sort of the season for these events, again, they are rare. And I've been forecasting ozone for the Sacramento region for 16 years now. And I can't remember the last time that we had one of these stratospheric ozone intrusion events in Sacramento. It is pretty rare, especially for that region, and especially because they are so close to sea level. That intrusion usually doesn't make it that far down into the troposphere. So a highly unusual event.
And just to add in here, not only is an event like this where you get stratospheric ozone all the way down to sea level, not only is that rare, but just altogether getting ground level ozone that's high, moderate, nearing USG in the first half of April in the Sacramento region, that's kind of hard to get as well too. So, not only are we talking about an ozone situation that unfolded in Sacramento, being of an unusual origin, just having moderate AQI ozone in the month of April, especially the early portion of April, that is few and far between as well, based on some of our climatology we put together.
Yeah, this is really the transport of ozone rather than what we're typically expecting, which is the production of ozone at the surface.
Yeah, that's a great segue. I wanted to talk a little bit about how the conditions here differed from what we normally expect for high ozone events. So you mentioned local production. That's usually what we see in the Sacramento area. That production would be from emissions of ozone precursors like NOx. On this particular day, we checked the NOx. It was very low. You also need the right weather conditions, or the typical ones that we look for are sunny and hot conditions that we see normally in midsummer. So this is early or mid-April. It's really unusual just in terms of timing, but especially looking at this satellite image, it doesn't match any of the conditions that we are normally trained to think about when we are predicting high ozone events. And I mean, like Jeff pointed out, the name of our podcast is High Pressure Podcast. We're normally drawn to these areas, especially of upper level ridges of high pressure that produce mixing and produce sunny and hot conditions at the surface. That's what we're attracted to as air quality forecasters. It's pretty rare that we would get excited about a cold front because it normally results in very good air quality, so that's just not as exciting for us. But in this case, it did the complete opposite because of one of these stratospheric ozone intrusions that transported that ozone from the stratosphere down to the surface. So even with cloud cover, showers, cool temperatures, there was high ozone observed throughout the Sacramento region.
This is a look at the 500 millibar map for the morning of April 13th. 500 millibars, for the layman, this is about 18,000 feet above our heads in the atmosphere. And at 500 millibars into the upper levels of the atmosphere, we had this area of low pressure that was off the northern California coast with a ridge of high pressure sitting over the Rockies. Typically, as air quality forecasters, we're more interested, as Patrick mentioned, in this ridge because that means reduced mixing and the potential for ground level ozone to increase. In this instance, though, it was this area of upper level low pressure that was really driving the bus when it came to ozone in the Sacramento area. And Crystal, you were telling us earlier that the way that this low was positioned the morning of April 13th actually put Sacramento in a prime place for stratospheric ozone. Talk more about that.
Yeah, so the low being cut off, so away from the main low pressure system off the coast of California, that is really the prime location for where these stratospheric intrusions happen, especially on the leading edge of that cutoff low. So really right there, right on top of Sacramento and Northern California is where you would expect to see a stratospheric intrusion if one were to happen with this cutoff low.
And just to add a quick anecdote from this morning, I was actually on our forecasting desk forecasting for Sacramento on this day. And I was noticing 9, 10 o'clock in the morning, we had, ozone levels that are around 57 to 60 parts per billion. And that was at 9, 10 o'clock in the morning, very early. Typically, with ozone in the Sacramento region, we see those levels sometimes early to mid-afternoon, not so much, 9, 10 o'clock in the morning. Patrick, both you and I were sort of drawn to this like hummingbirds, this GOES 18 air mass product. Talk about how this can indicate the potential for stratospheric ozone.
Thanks, Jeff. So this is a great animation that shows the different air masses in a particular area, and the red colors here indicate what's called high potential vorticity air mass. So that would indicate stratospheric air. That's where the potential vorticity, or PV, is naturally higher. And this indicates that that air is being drawn down into the lower atmosphere towards the surface. You can see that high PV air mass wrapping around behind this surface cold front. And it's exactly that kind of mechanism that brought this stratospheric ozone into the lower atmosphere and eventually to the surface. And this just illustrates it really nicely.
Steve, a look at the sounding from Oakland on the morning of April 13th. Also some indications that the potential for stratospheric transport of air down to the surface were existing through something called the tropopause.
Yeah, we can see the tropopause is indicated by the area in the top part of that profile where we see the temperatures actually start to increase. So the red line is temperature as it moves to the left. That's a decreasing temperature, but then as it moves up and to the right there, that's showing the temperature actually increasing, which is partly due to the ozone that exists in that part of the atmosphere. And so we can see that is where the interaction was taking place between the stratosphere and the troposphere. One thing, just looking at this compared to a normal sounding, we don't normally see that area between the 300 and 500 millibars. The lapse rates, or the change in temperature with height, is generally more stable in that region. But on this particular day, we can see that if we were actually to saturate that parcel of air aloft, it's actually pretty unstable. And so that allows air to mix more easily. When we have unstable air, it can more easily transport from aloft down to the surface. And so that could be one part of this system that helped bring that stratospheric ozone down closer to the surface than we would normally see.
So Crystal is our guru when it comes to stratospheric ozone intrusion events. That's why she's here for the High Pressure podcast. And one thing that she has shown us through the years with some of her analysis is through some of the computer modeling, you can actually get indications of a stratospheric ozone event. Crystal, we're showing the Wacom model here, stratospheric ozone on the left, carbon monoxide on the right. What does this tell you for a stratospheric ozone intrusion?
Yeah, so on the left, like you're saying, this is stratospheric ozone. So the ozone that's actually come from the stratosphere, that's now at 500 millibars. But on the right, you're also seeing that area where the area of high stratospheric ozone is on the left. You're also seeing very low carbon monoxide on the right. And carbon monoxide is more linked with anthropogenic emissions. So things like people burning fossil fuels. But in the stratosphere, we're not going to have those types of emissions. So when you pull down stratospheric air, it's depleted in these types of parameters like carbon monoxide. So for stratospheric air, you would expect to see high ozone from the stratosphere and low anthropogenic emissions like carbon monoxide. So this really indicates to me that this is definitely a stratospheric intrusion that went along with this low and this front.
And one of the things that we looked at from an air quality perspective is some of the other air quality modeling, like the NAQFC model. And that had no indication whatsoever that we were going to get stratospheric ozone reaching the Earth's surface. So, Patrick, these events, they are very hard to predict, but Crystal, the guru of stratospheric ozone intrusions, she can actually help air quality agencies out with this.
Yes. One of the things that a lot of people face with these stratospheric intrusions is that they have these high concentrations of ozone that are transported to them. And this ends up affecting their air quality, and then eventually, or in some cases, it affects their attainment of the NAAQS, the clean air laws. So they have to put together these reports, these exceptional event reports, and there's a mechanism specifically for stratospheric intrusions. And these would be some of the ways that we could show that this was ozone due to a stratospheric intrusion. Things like the Wacom model or the high potential vorticity map that was shown earlier. So lots of different ways to show these.
Crystal and her team have done a lot of great work for agencies analyzing these events after they happen and helping to establish whether it was what we call an exceptional event. But the question remains for us forecasters, can we predict these events? And unfortunately, the answer is probably not very well, because they are so rare, so unusual, especially for an area like Sacramento. So just to give you an idea of how the models, the air quality models, struggled with this particular event, the NAQFC model for the Sacramento region on this day was predicting a maximum 8-hour ozone concentration of 45 parts per billion. And here on the screen, we're seeing what the actual observations were. Now, 45 parts per billion is in the middle of the good AQI range. Here we're seeing values in the 60s and one up at Sutter Buttes, 69 parts per billion. That's on the very upper range of the moderate category, as you said earlier, Jeff, almost unhealthy for sensitive groups. So this is a model that is generally very accurate and helps us with our forecasts every day. And it really underpredicted the ozone concentrations on this day. I think there are certain challenges with getting the atmospheric dynamics right in these models and properly simulating that transport of air from aloft all the way to the surface. So that's an area where the modeling can be improved, and we can try to anticipate these events. But again, it seems like 99% of the time when we see upper level low pressure with a surface cold front and plenty of cloud cover, it's just going to be really good ozone. It's just these really rare conditions where we see a stratospheric ozone intrusion. So very difficult to predict, and there can definitely be improvements made in the skill of predicting them.
Yeah, I think that as we talk about forecasting, I think it's something that would be hard to predict, the next day if we're looking a day out. But I think there were some signs this morning of April 13th that, as we saw the ozone coming in behind the cold front, it first actually showed up in the Bay Area and then was transported into the Sacramento Valley. Using some of those new satellite tools that we have, it could be something that forecasters could react to for the same day forecast, and certainly bump that forecast up as those signs start to show themselves, because this doesn't match really anything that we normally see in the Sacramento region, because we had cloud cover, we had ozone widespread across rural areas that don't normally see ozone. They don't have the emissions to produce a lot of ozone even when it's sunny outside. And so to see how it spatially just impacted the whole region, how it was happening even early in the morning, happening during cloud cover, those were all signs that, hey, this is a different kind of event. Would have been really hard to predict ahead of time, but perhaps as we see those signs unfolding, can alert the public if necessary and let people know, hey, there's a rare event going on, and you might perhaps look at adjusting your activity today because of this. So.
Well, thanks for listening to and watching the High Pressure Podcast. To see some of the amazing work that we do here at Sonoma Technology, visit our website, www.sonomatech.com. Have a great day.